Here we have a crude picture representing an incline at angle of elevation alpha, that is angle alpha above the horizontal, this dotted line being implicitly horizontal, and a coordinate system, an XY coordinate system, right hand XY coordinate system, with the x-axis along the line of motion of a car that moves up or down the incline. Now the question, now the weight of the car is represented by this weight vector, this vector here. And the first question we want to ask is, what angle does this weight vector make with the positive x-axis as measured in the counterclockwise direction? Now, in other words, what's the angle theta in this picture? Because this picture is really what we call a free body diagram, or the beginning of a free body diagram. At least it's a diagram showing the weight vector in relation to the x-axis, which again is parallel to the incline and in the direction of motion of the cart, or at least parallel to the direction of motion of the cart. Okay, and using the circular model of the trigonometric functions, we measure the angles of vectors from the positive x-axis in the counterclockwise direction. Now, the question is, what's this angle theta? Well, there's a simple geometric argument, not all that simple. In the way geometry is being taught right now, I don't know how well people can do with this sort of reasoning, but this is being addressed to a class of mathematically adept students, so I think it should be no big deal. My grandson is right now in 8th grade taking geometry, and it'll be interesting to see if he comes out of the course with the ability to do this kind of reasoning. Okay, so what do we know? Alpha makes, the angle made by the x-axis with respect to the horizontal is alpha. The y-axis is perpendicular to the x-axis. The weight vector is perpendicular to the horizontal, and it follows in a way that you should be able to construct that the angle alpha also occurs here. So we have the angle alpha here, we have the angle alpha here, and of course that means we have it here, which means that theta is 270 degrees minus alpha. Again, the intended audience should have no trouble filling in the blanks here, but if you do have a question, it's a great question to ask using the question form. So there's the angle of W. Now, knowing the angle of W, we can easily calculate the projection of W onto the y-axis or onto the x-axis, but right now we're going to estimate that angle because we don't know. I haven't told you what alpha is. So let's just estimate what the projection ought to be. Well, to project onto the x-axis, we come over here, to the y-axis, I'm sorry. We come over here at what I hope is a right angle, and we get the projection WY. And then we come up here at a right angle to the x-axis, and we get the projection WX. Now that's kind of obscured by the indication of the angle, but you should be able to see what's going on there. And one principle of vectors is that a vector can be replaced by its projections onto the y and x axes, those projections being called the components of the vector. So since W can be replaced by its projections, we replace it by its projections. We put a wiggly line through the W vector, indicating that it's now been replaced by the WX and WY, its projections on the X and Y axis. But we could estimate, the WY here, I'll say the magnitude of the WY vector is probably greater than 0.9 times the magnitude of the W vector. And the magnitude of the WX vector appears to be certainly less than half the magnitude of the W vector, probably on the order of 0.3. Well, I got my head in the way of the whole thing. Okay, if we look at the WX vector, we say, okay, we can do it here, we can do it here, we can almost do a third one. I'd say it's somewhere in the 35 to 40% range. So maybe we could say, a question mark on that, but maybe about 0.37 times or 37% the length of the W vector.